Okay, let us begin. I've got a copy of the exams in there, in the chat, and we're going to continue from question 5. That double audio? Yeah, double audio is going. Good. The mute button on the Zoom interface had changed in a different spot. Question 5. Equation of the tangent to the graph of f at some point x equals a. They've put a little spot there to give you an idea of where a could be, but as long as it's between 0 and 1, we're happy. I don't think it's going to matter though as far as the procedure as to how we do it. The whole 0 to 1 thing. Reminder, this is tech active, so you don't necessarily have to solve the whole tangent line by hand. There is a function that can help you out with that a lot.
Is this derivative and then sub in A?
You can. You can do the whole proper tangent line method of finding the gradient, finding the point, and then rearranging the y take y1, or y take y1 equal mx take x1. You can do that. There is a guaranteed way of just getting it immediately, which is your tangent line function on the CAS. That's a bit easier, obviously. You then define f, comma x, comma a, because you're taking it at some a. You don't need a specific spot, as long as you have at least a value of x, whether it's a known number or not. It still works perfectly fine. And that'll get you the, that'll get you the generic tangent line. But yeah, you could have done what you said, which is to go through and get your gradient and point. But there's not a whole lot of like lines for that working out, so you might be a bit cramped when you do it. And so yeah, we get our tangent line formula as follows. Find the x-coordinate of q in terms of a. Q is over here, so it's going to be the x-intercept of the tangent line. That should be fairly chill once you have the tangent line.
Is it 2a cubed plus 1 all over 3a squared, comma 0?
Yeah, just a reminder that it asks just for the x-coordinate though.
Okay.
So we'll just give the x there instead. But yeah, I mean, that's about as basic as it gets. You've got the x-coordinate, let y equal 0, solve for x. Very chill. X-coordinate of p in terms of a. P is over here as the intersection between the linear and the cubic. Also a similar question.
Is x equal to -2?
Negative 2a.
Oh, -2a, yeah.
Yeah. Yeah. Did you already have a as defined as 1?
No, I just forgot to see it on the CAS.
Oh, sure. Yeah, yeah.
It was like -2 times a and just skipped over the a.
Yeah, yeah. Okay. Yeah, so if you do your CAS solve for the tangent line equals the cubic, you're going to get two possibilities. Only one of those is going to make sense for what we want. Obviously, you can see there's two spots at which it would cut. One at A, obviously, we're taking a tangent line at that spot. So A should be one of the solutions, we would hope. And then negative 2A, of course, is the only other one that could, well, that should be the P. Question D. Capital A is the function that describes total area of the shaded regions. So, well, yeah, this little bit between P and A, and then between A and Q. Find the rule of capital A in terms of little a. So 3 marks, so you're going to do a fair amount of that on the in handwriting. One's probably one of the slightly harder versions of doing bound area. It's not immediately obvious. Oh, maybe. It's slightly quirky. Yeah, I remember this one comes out to be quite a nasty equation. I mean, it is just a polynomial divided by a polynomial in the end, but it's a big set of polynomials. So if you start getting really big numbers, that's supposed to be. When we're doing bound area, one of the important things is to understand that we're doing essentially always going to be integrals of top take bottom. Whatever's on top, take whatever's on bottom. The linear is above the cubic for the entire duration from P to Q. However, one thing to consider is that what's considered the bottom isn't necessarily always the cubic. There's this right-hand side bit here where even though the cubic goes below the x-axis, the shaded bit does not. And so it doesn't actually follow the cubic the entire duration. There's a certain cutoff point where you don't want to use the cubic as your bottom. You want to let y equals 0 as your bottom, or obviously you just, it's 0, so you don't put it in there, and you're just doing the integral of the linear. The other thing to consider would be it kind of looks like you've got two predefined spots, left and right, when in reality, this little crossover bit here, you don't actually have to do this left side as its own separate integral. You can actually go straight from P all the way to some crossover point. So I guess what I'm saying is you don't actually need 3. You don't need one for here, one for here, and one for here. You can actually do it in 2 because there's no dip below. It's always above or equal to the curve. So to catch people up a little bit, one of the first domains you'd probably want to do would be negative 2a to 1, right? Because that's going to be the starting bit of p, which over here we saw that was x equals negative 2a, and that's going to maintain the entire way up until 1, because up until that x equals 1, the linear will be above the cubic the entire time. That'll get you the first integral. And so yeah, you do linear, take cubic, that'll get you the first section of area there. The next section, maybe I'll pause there.
Chris, why can't we do this one from negative 2a to just normal a?
Negative 2a to a. You can. It's just slightly inefficient, because then you got to do a bit over here and then a bit over here again. So if you do negative 2a to a, you get this. Perfectly fine. Then you'd have to get this and then this. Versus, because there's no actual crossover of curves here, you could go all the way from negative 2a to 1 and get two things in one go. It's just slightly more efficient. Anyone getting close to an answer, or shall I jump back in? Because
I
after you...
think I'm almost there.
Yep.
Yeah, I got like some insane division of polynomials.
Did it look like this insane division of polynomials?
Yeah.
Yeah. Yeah, that's all. So yeah, for the second domain, we actually already had that x value. We solved the x-intercept of the linear a little bit ago. So you're just doing that from 1 to that value. And obviously, because that's a nasty number, when you shove that in, you're going to get a bigger nasty set of numbers. And then, well, yeah, you found both area sections, maybe 3 area sections, depending on if you split it up 3 ways. Just, yeah, add them all together, and then the CAS will do some simplifying for you. Anything to clarify there further, let me know. Otherwise, feel free to move on to part E, because having that equation will be really helpful for this. You put it in F-min. For 2 marks, you'll get at least, you'll get a mark for it, yeah, and you'll be very comfortable with your answer, because F-min will absolutely give you that. I wonder if F-min will give you like an infinity though. Capital A, in terms of A, I guess just make sure you do, maybe A between 0 and 1 will matter for that. Let me just double check in the background. Did I do fmin? Yeah, no, I did do fmin. Okay. So if you do end up fminning it, you'll get that. Of course, just making sure you put, maybe that matters. 0 to 1, probably. But as far as getting the second mark there, you might want to just chuck in a derivative equals 0, just for the hell of it, to say, hey, look, I did some working. Because I think the exam report complains rather, about if you use CAS syntax for working out. Let me just suss that out real quick. 5e. Okay, they don't really mention anything about CAS syntax. Why? I vaguely remember something complaining about CAS syntax, but the things they mention in the exam report would be to put an a dash equals 0 in there and then get it. So to be safe, I would start with fmin just so I know I've got a guaranteed answer there, and then when I do my f dash 0, I can be reasonably certain which one of those is the min and which one of those is the max. But yeah, nice work. Part F. Consider the regions bound by inverse tangent to inverse this time. Interesting. At x equals b. B is also between 0 and 1. So now we're taking this graph of f, flipping it into, I guess, a cubed root graph. And, I mean, a is effectively b. It's still the same thing, 0 to 1. It's just an x coordinate from there to there. And the vertical axis this time. This is a bit cheeky. So they're using the vertical axis this time for the so-called floor of the function. Should probably spark ideas of using symmetries. Just gotta be really careful with how you do the symmetries. Because you can absolutely do this by solving the inverse, getting a tangent, and then casing your way to B, just like you would have done the entire way from A down to G, was it? Or E. But that would be slightly inefficient.
Guys, could you explain the symmetries?
Yeah. So F and F inverse are reflections about the line y equals x. Basically, what that ends up meaning for us is that we have a swapping of x and y. So the area that we have here is we have f, a tangent in the same spot, and it's got the floor of the x-axis as opposed to the y-axis. When we have f inverse, we're essentially flipping all of our x's and y's, and in the question, we're still putting the tangent at the same spot, which is sure, whatever, but now the vertical axis is the floor instead of the horizontal. All that to say, we can end up using the information of the previous question to... Yeah, that's not going to be satisfying. Let's just have a look. I was trying to keep it vague, but I feel like you'd be better off with the picture. So if you wanted to have a look at a picture in the real deal, you would get your inverse and then cas tangent line out of it. So just use the solve function on the cas to flip the inverse around. Tangent line cas will get you there, and when you draw them, they'll look like this. You'll notice now the floor is over here, and you do end up dipping a bit below. What you'll notice is that it looks very similar. In fact, it is the exact same area. So if you have a look at this bit and then compare it to what we had up here, it's as if you had chucked that like kind of underneath here and this bit up here. And so what we know is that the areas between them are identical. So that's one thing you can leverage. The final bit to leverage there is the fact that the x and y's are swapping. So we did this stuff earlier, which was, hey, what value of a minimizes our area? That's an x coordinate right there. And so even though we're looking for an x coordinate over here again, b, for which there is a minimum, because we've done all this flipping through the inverse, if we get the y, which would be at this spot, that in turn is the x for this one, because you're flipping from x and y. And so all I end up doing is I shove the x value from the previous solution into f of x. That gives me the y, and therefore when you go through your whole inverse procedure, that'll come out to be an x value of the inverse function. There's kind of like a bit of doubling up going on there. You don't need this whole graph. This is just purely for your own understanding of the question. If you recognize the symmetry, you can literally do this in one line. Go straight from here, f of that, and that gets you your x. The safest way by far, though, would be to literally just go on your graph, on your cas, get the inverse, retangent it up, and then chuck that in an f-min again. That would also work perfectly fine. So you don't need to use symmetries, but it definitely helps. Anything there left to clarify? You've got two main ways of going about that. If not, feel free to move on to F. Oh, sorry, that was F. G. Okay. Find the value of the acute angle between the tangent to the graph of F and the tangent to F inverse. Yeah. So I guess doing that whole procedure, finding the tangent to the inverse earlier would be helpful for this. Yeah. Angles and tangents. So then I have to understand the relationship between gradient being tan theta. That's going to be an important part of this. Or, your tan inverse of the gradient gets you theta. It's one key element there. You'd also probably want a visual. So I would be graphing the two separate tangent lines. One would have been the tangent to f, the other being the tangent to f inverse. And we're actually told at what spot x equals 1. So that effectively means a slash b is equal to 1, since those were just generic x spots we took tangents at. So you don't need to re-find both of those tangents. You could just chuck in a equals 1, b equals 1 into what you already have. That'll save you a bit of time. So if you were to go and grab both of those tangents, um, the tangent to f is going to come out as negative 3x plus 3 if you shove in your a equals 1. And the tangent of the inverse will actually just end up being a vertical line. Because if you take it at x equals 1, what you might notice if you had already solved the inverse, or if you've seen the graph of it, there's actually a inflection point there. And it becomes instantaneously vertical at that spot. And so for that reason, you actually end up with just x equals 1 as the second tangent line. From there, we just care about the acute angle between the two. I'll pause for a little bit longer so you can have a stab at it before I give away the picture, because I've also annotated it, unfortunately.
This is it 18. Never mind.
Maybe. Hang
I
on.
was about to say 18 degrees, but no, I think it's wrong.
Yeah, let me double check actually. I think you got it right. Yeah, 18.43.
Yeah, 18.43.
Yeah, I think you got it right. We do want exact though. So what method did you get your decimal?
It was tan inverse 1 on 3.
Yeah, okay, so you would just leave it as tan inverse 1 and 3 then. Yeah. Yeah, that was it. So if we have a look at the picture, what was going on, if you draw those two tangent lines, the acute is this thing in here. So in order to solve that, you basically have to leverage the fact that we know a vertical line has a 90-degree angle, so that can cut out a decent portion of it. And we can also find quite easily the angle of the linear by just doing tan inverse of negative 3. And so all in all, to get the acute part of that, you've got 90 taken up here, so whatever's left over is, well, therefore there. And so yeah, that's pretty much it. They'll end up cancelling out, and so you get tan inverse of a third in that. Cool. Anything to clarify further there, let me know. Oh, actually that's going to be the end of the exam there. So I guess while I pull up the next one, have a think if you have any questions. That 2018, we're going to... will we get through all of them by... oh, probably. We might end up on 2017 before the year 12 exam. All right, tech free. Okay. Chuck both of those in. Skip question 1, those are chill. Question 2 is the same thing. Question 3, yeah. Question 3 is probably a good place to start. Solving a circular function over a particular domain. Very common question. Right, that's about as standard as it gets, actually. You're just doing from 0 to 2 pi. No composite function to mess anything up. It's just where does cos equal something?
Is it 2 pi and 3 and 4 pi and 3?
Those are it? Yeah, absolutely. Rearrange to get cos equals negative half, and then from there, where does cos equal negative half in the unit circle? Easy. Sketch the graph of f. So f is the 2 cos x plus 1. Sketching it. Yeah, okay. That should also be fairly quick. And it's 3 marks, so we really save. Yeah, we save time on this one. Label endpoints local minimum. Mm. Yeah, okay, this one was very free. As long as you are confident enough in your ability to sketch circular functions. There's that like horizontal translation, so it's still just 0 to 2 pi. Yes, there is a vertical, which would normally be a pain in the ass, but our answer to A actually helps us quite a bit here in saving some time. And they've even provided the scaling on the x-axis for us already, which is nice. Now, it turns out to be a little bit annoying because it doesn't give us exactly quarter period, but it gives us the stuff that we ultimately end up wanting.
It's going to be a cos graph starting at 3, and yeah, accepting a 2 pi and 3, 4 pi and 3, and the lowest y value is just -1.
That's it. Yeah, and you get that at pi. Yeah, so I've drawn just like a very standard version of how you would do that if you had no prescribed axes. You would, do your full period 0 to 2 pi. What's that? Focuses, of course. Split it up into 4 bits. Cos starts at peak, and then, dot everything out. And because we've already solved the x-intercepts from before by letting the y equal 0, we can just borrow those from earlier. Cool. And yeah, obviously would label it, but I did not label mine. Normal distribution in a tech-free. So there's only really one way we can solve these kinds of questions when it's tech-free. Got to use the approximations. Yeah, 68, 95, 99% rules. First one's a freebie, if you really pay attention to it. Normally distributed with a mean of 6, variance 4, find probability x greater than 6. Or in other words, x greater than mean. Yeah, 50%. That's right. Yeah, so if you draw your normal distribution with the mean and you say, yep, I want to be right at the mean, cool, that's a 50%, because obviously the symmetry of the normal distribution. Very good. B, a little bit challenging, because now you're going to do the whole comparison between the regular and standard normal. One of the first things I'll be focusing on is getting the inequalities to point the same direction. That way you can much easier compare the two things together. Something like this would be a good start. If you have a look at the handwritten section, I've drawn the two distributions, the x and z's. X greater than 7 and z less than b are supposed to be the same thing, so I've tried to proportionally draw those out properly. Pointing right for the x and then pointing left for the z. Those are supposed to give the same area. Challenge is they're pointing in different directions, so one of the things we want to start working towards is figuring out what's the equivalent x over here to at least get them as comparable pairs. Right? We got an x and z that are directly comparable versus on the other side of the distribution. Five? Yes, it will be 5. At least this point here will be. Yeah. Because area 1 right of me with the same, area 1 right and pointing right is the same as area 1 left and pointing left. And so yeah, that spot's going to be 5. So we have an x of 5, we have a z of b. We got to figure out, there's an equation that lets us flip between x's and z's. That'll be a good idea. You can also kind of hack the final answer a little bit without having to go through all of this. I mean, you got to get to this stage, yeah, or maybe even just before the flip. You could probably solve it a little bit earlier, but we'll go down a standard route first, and I'll show you a few hacks. Anyone getting close to an answer, or shall I jump in? Yeah, sure. So here is the z equation. It allows you to convert from z to x as long as you know the mean and standard deviation. So we have z is b, we have x is 5, that's good. We have the mean is 6, that came from the question. You just got to keep in mind we had variance 4, so just make sure you square root that to being standard deviation of 2. And then when all is said and done, you've now solved your b value. B is negative a half. That's a very mathematical sound way of doing it. You do your symmetries, you chuck into the z formula, and you get your result. The other thing you're basically doing the same math, but just more conceptually rather than formally written on here. It is a 1 mark, so they only care about the answer, so you can sort of use these little hacks to help, which is to say, okay, area right of 7 is the same as area left of b. Cool. How many standard deviations did I move right here? Well, if my standard deviation is 2, and I've gone from 6 to 7, I've moved half a standard deviation right. So whatever's over here must be half a standard deviation left, and since z numbers are effectively standard deviations, I should get b equals negative a half. Now you are still doing this math, like in your head you've done, oh, it's only 1 standard deviation, sorry, it's only half a standard deviation right, and you are kind of already doing this math, just a little bit informally in your head. So, not really a hack, but kind of feels like it's faster. Anything to clarify there? All we ever do in these circumstances is make sure we're pointing in the same direction and then using a z formula to, to get the equivalence. So you can't really do anything comparing z to b, 7 to b. You have to be either flipped over to the side or have to use little, either do it in your head, I suppose. Is there any way I can really say that? Cool. Let me know if I should clarify. Otherwise, question 5. State rule and domain of F inverse. That'll be chill. 3 marks for it? My god. I reckon I can do that in like...
I was doing the inverse whilst you were explaining the last question.
Yeah.
And it comes out with like 2 plus minus 1 on root x. It's like
Yeah.
a
Okay.
weird thing.
Yeah, I can imagine why, because you're square rooting. Look at the domain of F. It's not a full truncus, it's the right-hand side of the truncus. So only one of those roots, the positive or negative, will actually be applicable.
Yeah, I'm guessing it's the positive.
Probably. Yeah, because it'll go up like that. That way. Yeah, that seems right to me. Just sort of based on the visual of what that would look like. Because if we have, what is it? It's a truncus at 2. So you have your asymptote here-ish. You got your y equals x, and so the equivalent root the flip. So this goes over to yeah. That way, the you're asymptoting out there, which means it would asymptote over here. Maybe it's a negative root actually. Maybe it is a negative root based on my poor attempt at trying to draw it inverse. You can figure it out quite quickly by making sure range and domain flip according to the right thing. So for instance, the domain of 2 to infinity should now be the range of your inverse. So when you think about, no, it's going to be the positive root then, because it's got to go up. So I don't know what I've been drawing here, but yeah, domain of original should be range of inverse. So for it to go 2 to infinity, it would have to be a positive root. Negative roots would only ever go down. Cool. Did you have a set of values for it?
As in like the domain.
Yeah, domain and rule, I guess, are the two things.
I thought the domain would be 0 to infinity.
That's correct, yeah, 0 to infinity. And that would have meant that you probably got the inverse right as well. What did you get for inverse?
2 plus 1 on root x.
Yeah, that's good. Cool. Let's have a look at that. Domain of inverse would just be range of the original. So we can quite clearly see range of original, 0 to infinity. I guess I did kind of draw mine just sort of floating up quite high up the x-axis, but yeah. And then yeah, as far as the math goes for that, they were kind of light on it. But yeah, you're just rearranging for x there. You'd done y equals that, swap them. You'd have x equals those. Multiply the denominator, square root the other side. Yeah. If anyone wants to see the full math written out, let me know. Otherwise, feel free to move on to. Oh wow, that was it. Question 5 was just that. Nice. Back to probability. Question 6.
Is it going to be 3 on 4?
3 on 4. Which one are we specifically doing? Probability of black. 3 on 4, yes. That's it. Nice. Couple of ways you could have done that. What was the way you did?
I just like visualized a tree diagram in my and every single stone has a 1 out of 8 possibility of being chosen. So if there's 6 black stones, that means it's 6 on 8, or otherwise 3 on 4.
Oh, okay, cool. So you've ignored like the whole box 1, box 2 thing and just sort of went straight for imagining all separate stones. Yeah, okay. Sweet. This one was done ever so slightly differently in the tree diagram in the sense that they had like branches for box 1, box 2, and then each of these outcomes afterwards. But because these are 50-50 split, it doesn't actually matter to have these. You can absolutely just look at the right-hand side and be fine. And the last way they've written down is just find probability of white and then do 1 minus. Cool. Part B. It is not known from which box the stone has been drawn. Given that it was black, what's the probability of box 1? Yeah, this we're having a good tree diagram probably helps.
Two on three.
213 was real fast. Cool. Let me double check. Yeah, 213. That is correct. How'd you go about that?
I mean, it's just about like shrinking your sample size, right? When you have
Hmm.
conditional probability. And
Yeah.
if this, so that means like your new denominator is going to become six because it's only six black stones.
Yeah, because given black, you only look at the black outcomes.
Right. And then out of that, four of them come from box one. So four and six is two and three.
That's a really good way of doing it. Yeah. The whole Venn diagram approach almost, which is, yeah, you restrict your sample size and then go from there. Brilliant. Yeah, I love that. That's good. Um, a more conventional way would be to do your whole conditional probability formula, where you find the intersection of the two and divide by the conditional. That's going to be a lot longer, obviously. So it's good you're able to spot the fact that you're restricting a sample size. Very good. Nice. Look at that. We blitzed that out in like, what, under a minute? If you cut out the time of me talking. 4 marks in a minute. Hell yeah. It's real good. Question 7. Think of maybe 2 ways you can go about this. Minimizing distance has a very standard way of going about it. Get your distance equation and then, your whole derivative approach to find stationary points. Because it's a linear, you have a bit of flexibility, I think. Yeah, you have quite a bit of flexibility actually. Yeah, if you do derivatives, if you do the whole get distance equation and then derivative 0, solve for x, sub back in for y, you're going to run out the full time allotment for that question. There is a hack for it though. Getting close to time, so I think what I'll maybe do is, unless someone's close to an answer. Anyone close? Okay. So, the whole distance formula thing works, absolutely. You can do the whole take a generic point on the linear and the origin, and then, you're just using Pythag, derivative 0, and you'll get there. The thing to notice specifically with linear is that minimum distance is going to be perpendicular, a perpendicular line connecting them. And so one of the things you can do quite quickly there is, because it goes to the origin, you have to think like next to no thoughts to get the equation of that perpendicular line, because 0, 0, you just got to think what the gradient of the line is going to be. And it's going to be -1 over the linear that you have. And so with that in mind, we can now just say, cool, where do those things intersect? And that is very quick and easy to do, versus having to differ root using chain rule. Is that 2 chain rules? No, it's just 1 chain rule. Make it equal 0 and then go from there. Whereas this is, well, much clearly faster. Try that one more time. Clearly much faster. That's the order that's what it's supposed to be in. And so yeah, that's one little hack you should probably know for linear. If it's anything else, like if you had like some sort of quadratic here or whatever, just some squiggle. Yes, it's perpendicular at this. Is it always perpendicular? No, it's probably not always. Because if I had drawn a quadratic like that, had a turning point there, then that wouldn't work. You would have to do def 0. Because yeah, that would definitely still be the... Might not even be the minimum there, actually. But yeah, so when it's linear specifically, you can make use of that. Anything else, you'd definitely want to stick with distance formula and derivative. That's about it. Any questions? I'm happy to stay behind for a little bit to answer them. Otherwise, yeah.
Chris, about the linear hack, right?
Yeah.
Isn't it possible say that same like linear line was a lot more steeper than, but it was still intersecting a -4? Wouldn't there be a point where the line might be closer elsewhere than on like at like a straight line on the origin?
Yeah. I didn't put a x there, right? There's actually no scale on the x, so this can be as steep as you want to imagine it. So, if what you'll notice is that because we know it goes to the origin, that's why it maintains perpendicular. If it was any like out here or out here, then yeah, you've now got to play with that. But because it goes to the origin, yeah, you're perpendicular to this line. So let's say I draw a separate set of axes that looks visually different. I draw it quite steep like that. Perpendicular doesn't mean this same like it was here. Perpendicular adjusts. Oh, whoops. Perpendicular now adjusts to be like that, or something like that. So perpendicular doesn't necessarily just mean it maintains that gradient. As your gradient changes, so too does what the perpendicular distance would be.
All right, cool. Thank you very much.
No worries. Happy to help.